Okay, students, we are into the text video lecture. The important point here is, before we start, to do any quantitative metamorphic work, the first thing that you try to do is find out the pressure temperature conditions. So I just gave you a little bit of an example of how PT conditions are determined in a rock. Essentially, the PT conditions are found from the compositions of the rocks, and you can treat them thermodynamically. So essentially, they become a sliding scale equation where if you change the composition, the position of the reaction changes in PT space, and from intersection of two such reactions, you can calculate the PT condition in the rock. This is the primary objective, and not the primary, the first thing that you can do in numerical phase metrology. Find out the pressure temperature condition. And whatever you do before, it follows. But the first thermodynamic variable that you retrieve is the PT condition of a rock. Now, I must tell you the following thing. We have just found out the PT condition of a rock. But if you have, say, zoned minerals, then of course you can understand the compositions of the mineral phases changes. And you know now from your experience that if you change the composition of the phases, the equilibrium condition changes. Right? So obviously, if you have a rock, a sedimentary rock that is deposited, say for example, a sedimentary rock that is deposited on the surface of the earth, and then during some tectonic process taken down, and then you see the rocks today exposed on the Earth's surface, it has gone through a cycle of pressure temperature changes, which could be one continuous process, or which could be essentially a product of multiple metamorphic processes spread in time. Now, these are more complicated issues, and I think for this class, metamorphic phase equilibria, it is better, given the time, that we don't go into this, for it would require much more, and we have not even started metamorphic petrology. We have been dealing with thermodynamics, and we need to finish this. So, but now that you have been given an idea, I think in your advanced level course, if you choose any, you can do that part. But for the moment, we move over from pressure temperature condition. After we find out the pressure temperature condition, what next? Now for that, let me start with an example. A very common example. Say for example, you have muscovite, biotite, garnet, sylvanite, quartz, magnetite, and ilmenite. A very, quite a common assemblage, if you tell me, a very common assemblage, which is an amphibolite species, and it is at temperatures below where muscovite breaks down. So essentially, it's not the high amphibolite species conditions, not in terms where muscovite breaks down to. Okay, I think we can do this. We can write K feldspar, for example, just to make things simple for us. So we have this assemblage. So you still have muscovite. So you are essentially still. Just 1 second before I come in. Just 1 second. Yeah, if we have this assemblage. And now, for example, you know that its formula, let's go to simple things. AlSi3 O10 OH whole twice, that's the formula. Biotite, you know it has the common formula KMgFe whole thrice AlSi3 O10 OH whole twice. That's a very common formula. We don't go into more complications. Let's see, for example, we have CaMgFe 3Al2Si3O12 sillimanite, you know, quartz, you know, magnetite. Okay, I think I can take this, the plagioclase. So we have Na, Ca, Al, Si 408. This is 1, that's 8. Remember, albite is Na, Al, Si 308, and anorthite is Ca, Al2, Si 208. Now we talk a little bit about magnetite and ilmenite. I have not talked about it. I think you know about it, but it is better that I introduce you before there is a complication. So you have a triangle, compositional space, where you write FeO, Fe2O3, and TiO2. These are the 3 component systems. So as you know, this is hematite. This is hematite. This is rutinum or anatase. And WO is very close to the formula of woostite. Very close, not actual formula, it's woostite. So woostite, FeO, TiO2, Fe2O3. And if you take the midpoint here, FeO, TiO2, then you have FeTiO3, which is ilmenite. Right? And then you have FeO and Fe2O3, and this gives you Fe3O4, and this is magnetite. This is magnetite. And here you get another phase, which is FeO plus 2 TiO2, and therefore we have FeTi2O4. And this mineral is called Fe. No, sorry. I'm very sorry. Here. Sorry. This mineral here. Fe2TiO4. So actually it should be 1/3. It's just a little high. So this mineral is called ulvospinel. This mineral is called ulvospinel. Now in this triangle, compositional triangle, the magnetite is a solid solution between Fe3O4 and Fe2TiO4. I'm writing here. So this is FeO, Fe2O3, right? This is FeO, Fe2O3, and this is 2FeO, TiO2. So this is the solid solution between magnetite and ulvospinel. These are a solid solution series. There are more about it. We don't go into the details. And there is also a solid solution between ilmenite and hematite. So that means ilmenite, FeTiO3, and hematite, FeFeO3. Hematite is Fe2O3, so it's FeFeO3 and FeTiO3. The substitution here you can see is, this is the substitution. Fe and Ti is the substitution. So this is ilmenite, this is called the magnetite solid solution series, and this is called the ilmenite solid solution series. So these are the two end member phases. So magnetite can be written in terms of Fe3O4, Fe2TiO4, and ilmenite can be written in terms of Fe2O3 and FeTiO3, whereas you have rutil here. So this is your phase assemblage. So we take this phase assemblage and keep it for some time. So now you know your minerals are muscovite, biotite, garnet, sillimanite, quartz, magnetite, ilmenite, K feldspar, plagioclase. I have deliberately made this bigger so that it will be easier for us to deal with certain reactions. Now you know that we know how now, I think now by this time you have become experts in finding out system components and phase components and phases and degree of freedom and number of independent reactions. Now you can do. So as soon as I give you the compositions, you can derive all those parameters, including independent reactions, and you know the Gibbs phase rule, the number in the Gibbs phase rule, degree of freedom, plus number of independent reactions should be equal to the number of mathematical variables. If there's a disparity in the two, you can't retrieve data. Right. So now we have this assembly. So if somebody asks you, how do you find out the pressure temperature condition? Obviously, as discussed before, we should look for reactions involving solid phases. That's the first thing you should look for. If I want to find out the temperature, immediately you look at this and say, okay, this has to be a solid reaction, so a fluid-free reaction. And you know that delta P by delta T should be infinity, so delta VR of the reaction should be very small, and for which you need exchange reactions. So you can see your biotite and garnet produces an exchange reaction. This yields an exchange reaction. Biotite and garnet. So you can find out the temperature from Mg Fe exchange between biotite and garnet. Mg Fe exchange between biotite and garnet gives you an indication of the temperature of the rock. Now for the pressure, again, you ask yourself, I need a reaction that involves no fluids. I need a reaction that does not involve any fluid phase. And it should have a reaction with a large delta V. Why? Because if you have a large delta VR, then the dP by dP, or the Clausius-Clapeyron slope, it should be equal to 0. So that is why you need a reaction where it is expected to be a large volume change. Now you know, garnet, for example, is a mineral which is very dense. So it has a smaller molar volume. So it would be important to involve garnet as one of the reactions. What are the possible reactions? You can see, say for example, you look at this part, you look at the garnet, it has grossular pyroalumine, right? So if I have to take a garnet component, say if I take grossular, then the only way that I can compensate it is by calcium in plagioclase. So I write a reaction, say for example, Ca3L2Si3O12, that's grossular in garnet. And then on the other side, of course, you have to have CaL2Si2O8, the anorthite component in your plagioclase. And if you do that, and if you're balancing calcium, because there's no other phases which involve calcium, so you actually have 3Ca2Si2O8. And if you do this, then you will have 6 aluminium here plus 2 aluminium here. Now you can see you can balance it with 2Al2SiO5 or sillimanite. Do you understand? So now you see here your calcium is balanced, your aluminium is 2 into 2, 4 plus 2, 6. Here it is 3 into 2, 6. If we look at silicon, this is 3 and this is 2, 5. Here it's 6. So plus SiO2. And this should give you a fluid-free reaction, not a fluid-absent reaction. Fluid-absent reaction does not mean fluid-free reaction. Fluid-free reaction involving grossular aluminosilicate quartz is equal to anorthite. And you can already see, since garnet is on this side, it should be the high pressure phase, because garnet is dense, so it should occur in the high pressure phase. So this is one reaction that can be written for estimating pressure temperature condition. Is there any other way that a pressure temperature condition can be found out? We have to look. So say for example, if I involve say muscovite and biotite, say for example I involve KAl2 AlSi3 O10 OH whole twice. That is muscovite. Now if I have to have a fluid-free reaction, no H2O comes out of the reaction, then I should need to balance OH2 here. And if I have to do that, then the only way I can do it is I can write KFe3 AlSi3 O10 OH whole twice, and this counterbalances it. You see, OH2 and OH2 and potassium. So, you know, if this balances, if you always keep the same stoichiometric coefficients here, then the reaction is always balanced. But the other phases are not. Say, for example, you take Fe3 and you don't have Fe3 anywhere. So you take the Fe3 from garnet. So if you write plus Fe3Al2Si3O12. So now you write Fe3Al2Si3O12. Now you have balanced potassium. You have balanced iron. Now if you look, you have already balanced H2O, but it doesn't matter. If you don't change the coefficient, it will always remain balanced. And this here you can see 2 aluminium plus 1 aluminium, 3 aluminium plus 2, 5 aluminium. 5 aluminium on this side and 1 aluminium on this side. So we can write plus 2Al2SiO5. That's all of that. So you see, you have taken care of aluminium as well. Now what remains is silicon. This is silicon 3 here. This is 3. 6 silicon on the left hand side. 3 silicon plus 2 silicon. 5 silicon. Add 1 more silicon. And you have a balanced reaction. This also has garnet on this side. So this reaction that you you could use it for estimating pressure. You could use this reaction also for estimating pressure. You could have also changed Fe3 by Mg3. Have you understood? You can change, instead of writing from the Fe end member, then of course if you write from the Mg end member, you have to change it to magnesium. So it's a magnesium end member reaction. So you can take it either iron end member reaction or the magnesium end member reaction. The reaction remains the same. So here, for example, you are using the grossular component along with sillimanite and quartz to produce anode type component as a barometer. Here, you take muscovite plus garnet, gives you biotite plus aluminosilicate plus H2O, and you can use both the iron and the magnesium end members of the reactions. So you can see that with this theoretically, technically, you will be able to find out the pressure temperature condition of the rock. Ideally, they should give you one spot on the pressure temperature PT space. But it's not. There will be uncertainties, there will be errors. This is another aspect which we don't need to bother ourselves now. But you can see from this assemblage, I can find out the pressure temperature condition of the rock, which is our first goal. Right? Okay, now, what else can we find out? What else can we find out? Now here you see, you have hydrous phases. So obviously you can think of reactions that involve fluid, not fluid-free reactions now. You have done with it, you have found out the pressure temperature condition. So somewhere in your book, this is the temperature and this is the pressure, and you have taken a particular reaction, you have taken another reaction, and you have come to this point. You have a pressure temperature condition. Now your objective is, okay, I have the pressure temperature condition. What more can I extract from the mineral assemblage for that equilibrium pressure temperature condition? What extra information can I extract out from the rock? Now you see, you have hydrous minerals. So obviously you can write a reaction whereby H2O comes out as a phase component. H2O comes out as a phase component. Let's see, for example, as written, Kal2AlSi3 within bracket O10OH whole twice. And if this is the assemblage, then I can write here is equal to KAlSi3OH plus Al2SiO5, which for us here is siliconite, plus H2O. So here you can see you have 3 silicon plus 1 4 silicon, you have 1 silicon, so you have plus SiO2, which is quartz. So I can write the reaction balance. What is it? Muscovite plus quartz is equal to K feldspar plus aluminosilicate plus H2O. Okay? I will erase this so that we can use this part of the board. Okay. Let's say this reaction. Temperature, pressure. This reaction has a shape like this. This I discussed before. There is a gentle slope and a steep slope. At the higher pressure, you have a steep slope. Remember, if you draw a tangent here, this tangent is dP by dt, and if you draw a tangent here, it's dP by dt here. Then here you see dP by dt is low. Here it's tending to infinity. I told you why? Because the molar volume of H2O, here you see the molar volume of H2O. H2O is an extremely compressible material. So what happens? At low pressure, it has a large volume. So, if I take dP by dt is equal to del SR by del VR, then at low pressure, the delta V is very large because H2O is a very large molecule. So you have a very large delta VR and therefore the slope of the reaction is zero. But what you do is you bring in compressibility and incompressibility factor, and the molar volume of H2O decreases dramatically with increasing pressure. So what happens? As we increase the pressure, the delta V term becomes smaller and smaller and smaller. And this causes dP by dt to be very steep, and that is why you have an infinity value. So this is we have discussed before, and we can now start with something else. So the reaction has a slope like this, where you have muscovite, quartz, and you have K feldspar, siliconite, and H2O. Now, this XH2O value, this XH2O, if you reduce XH2O, this I also discussed before, based on Le-Chatelier's principle on law of mass action, if I reduce activity of H2O, then the reaction moves, H2O is on this side, if you reduce the activity of H2O, then the reaction moves to the opposite side. So what happens is, if you reduce H2O, then the reaction moves like this. So this is XH2O 1.0, this is 0.8, this is 0.6, this is 0.4. This is 0.4. So what happens is, say for example, this is your pressure temperature that you determined. let's say this is the pressure temperature of the rock you determine from the exchange reaction and other reactions that I know. Say this is the pressure temperature reaction. Now you see the position of the reaction muscovite plus quartz is equal to K feldspar plus sillimanite plus H2O. The position of the reaction is very different. Whether there is a fluid phase, whether it's a fluid absent condition, without that, this reaction XH2O, with the XH2O value, the position of the reaction changes in pressure temperature space. Remember, the reactions that we used to estimate pressure temperature conditions, they were fluid free, so they don't move. They are irrespective of the fluid conditions. But the H2O bearing reaction, of course, changes. And so depending upon the activity of H2O at different places, or we can put it as mole fraction, we take ideal mixing, although it's not, but we do take ideal mixing. And then the curves occurs like this. Now you can understand, if I take this curve and say this is 0.7, this curve passes, or this muscovite plus quartz, PT loci of this reaction, muscovite plus quartz is equal to K feldspar plus sillimanite plus H2O. The loci of this reaction at XH2O is equal to 0.7, passes through the pressure temperature condition that you have estimated. And therefore, you can find out XH2O is equal to 0.7 for that equilibrium at this pressure temperature condition, where these phases are equilibrium. So for these phases of equilibrium, for these compositions, for this PT conditions, XH2O value should be equal to 0.7. So you can see this is how physically we look at the thing. How do we look at it numerically? You see here. You remember, I'm erasing this. So you remember, if I took a classically, it should be delta GR is equal to 0, is equal to delta HR 0, minus T delta SR 0, plus P delta VR 0, plus RT ln. Now you see, activity of K Al Si3O8 in K feldspar into activity of Al2SiO5 in sillimanite into activity of H2O in the fluid divided by activity of Kal2Si3O10OH whole twice in muscovite into activity of SiO2 in quartz. That's how the thermodynamic written is reaction. So now you see, if we take aluminium this as a pure phase, sillimanite, which we normally take, so this value is equal to 0, this value is equal to 1. Activity quartz is always equal to 1. So now what will happen here? For this reaction then, we will have 0 is equal to, or maybe what I can do is, here you see activity of H2O in the fluid, and if we take this mole, instead of taking the activity terms, I told you the complication with activity terms, if we take the mole fraction terms, it's easy for you to conceive. So we will take the mole fraction terms, and if we do that, we can write 0 is equal to del HR0 minus T del SR0 plus P delta VR0 plus RT. Now I have RT ln X potassium in K feldspar into divided by X K Al2 etc. in muscovite into XH2O in the fluid. This is how I will write it. Why? Two things. I have taken out the pure phases and I have taken ideal mixing for everything so that it becomes easier. Because if I keep on writing activity, then you come into the gamma terms and that makes the reaction a little bit opaque to see what is actually going on. Mole fraction is a much more determinable term and a term which is familiar to you. So we have used this discourse. It's not the right thing to do, but it helps in understanding the thing. And you can always extend it to non-ideal mixing. So this is how the reaction looks like. And so now we can write, therefore, XH2O is equal to No, sorry. Let me write it, then I will explain. This is how we can write. What did I do? I took this whole part. You see there are no compositional terms here. I took this whole part to the left. So there was a negative sign. This is the negative sign. And then I had divided this by RT. So it's minus 1 by RT. And then I took the exponential of it. So this becomes exponential. And this one should then reverse and come here. So this is how XH2O, your equation, looks like now. So this is how the equation looks like now. There are two parts to this. One is this part. It does not involve any composition terms. And this part, which involves composition terms, mole fraction terms, activity terms, and activity coefficient terms. Activity coefficient is not here because we have taken ideal mixing just to make things simple. So you can see your XH2O in the fluid can be written by transferring this to the left hand side and hence the negative, then dividing it by RT and then exponential of it and then multiplying this into the reverse side. So this is all what you get. This is all what you get from the earlier expression. Now if you see here, in this term now, in this expression, these are thermodynamic terms. These are thermodynamic terms, including R. And since you know pressure temperature, these terms are all known. So, if you know the pressure temperature and the thermodynamic term, there's a constant. This is a constant. Because the thermodynamic terms are known, underlined by red, and the blue lines show the variables, pressure temperature estimate, that you did. And so, you know the pressure temperature condition, and so this is a constant. Now you see, the XH2O value therefore now, at this constant P and T, is a variant of the composition of the phases, two phase components, Muscovite and K-feldspar. Muscovite and K-feldspar. These are the two variables that dictate XH2. If they were, say for example, if they were pure phases, then XH2 can be determined straight away. And that would be the line, which is the red line. You will be at this point because you have taken this pressure temperature condition. If you change the pressure temperature condition in another point, you will get the same curve but in a different position. Can you see? You take pressure temperature condition and you will have a graph. You will have the graph, you know. Or for example, if you want to draw, say this is pure. And you have a particular XH2 value. You want to find out the position of the curve for XH2 is equal to 0.1. Then XH2 is equal to 0.1, 0.7, this is known. Now you put a p-value, t-value, you will get a p-value. You put another t-value, you get another p-value. You get another t-value, you can get another p-value. And so you can generate the whole curve. The curve for XH2 is 0.7. But when you are in a mineral assemblage, your XH2 you don't know. Your XH2 you have to find out. So if you have to find out, then pressure temperature has to be known before. And this is how you find out XH2 condition of the rock. From simple thermodynamics, this part is for the pure end members, this part is for the solid solution end members. Right? So if you know the composition of Muscovite and K-feldspar, you should be able to find out what is the XH2 value. That, in other words, looking at it the other way, this would correspond to this curve which passes through this pressure temperature condition. You can look at it any way you want. But the fact remains the same. The only thing extra that I added was, say for example, if this is pure, and you want to find out, how will you find the graph for XH2 0.7? Then you know XH2 0.7. So XH2 is 0.7. And what is unknown then? Temperature and pressure, because thermodynamic terms are known. So if you want to find out temperature, put in a temperature value, you get a pressure value. Put in another temperature value, you get another pressure value. Put in another temperature value, and you get a pressure value. And so you can really draw the curve. No problem. So this is how, not only there is one reaction, there are other reactions that can be written. Technically, they should give you the same XH2 value. So from the pressure temperature value that you determine from two fluid-free reactions, using that pressure temperature, now you extract XH2 value. Now you extract XH2 value. Okay? So now for this assemblage, you know pressure, temperature, XH2. Now the question is, can you find out something else? Let's see. We can use the same technique. You see here, there are two phases, magnetite and ilmenite. And as I told you, ilmenite is a solid solution between Fe2O3, hematite, and FeTiO3. And magnetite is a solid solution between Fe3O4 and Fe2TiO4. This is called hematite, this is called ilmenite, this is called magnetite, and this is called ulvospinel. Magnetite is a solid solution between magnetite and ulvospinel. Ilmenite is a solid solution between magnetite and ilmenite. There are complications in this, solvers, etc., etc. We ignore this for the moment. Now say for example, you know there is a famous reaction. It is, you must have read it somewhere. Fe3O4 is equal to Fe2O3. If I write this, then for example, if I balance for iron and if I balance for or iron. Then this is the reaction. So you have 6 Fe and 6 Fe. It's balanced. But you have 8 oxygen and here you have 9 oxygen. So you have plus half O2. Plus half O2. Remember, you know the pressure temperature condition of the rock. So if I do it this way, then I can write delta GR is equal to 0 is equal to delta HR0 minus T delta SR0 plus P into delta VR0 plus RTLN. If I write in the ideal mixing conditions, then I write X Fe2O3 in ilmenite divided by X Fe3O4 in magnetite into XO2 in the fluid. Now there is an error here. Okay, if I write activity, then Fe2O3 should be cubed. If I write activity here, this should be squared, and then XFeO2 should be half. This is how it should be written. So what we have now is equal to, so if I keep the compositional parameters on one side, so now you can see you will have activity of Fe2O3 in ilmenite whole cubed divided by activity of Fe3O4 in magnetite whole squared into activity of O2 in the fluid to the power half is equal to exponential minus 1 by RT into del H0R minus T del S0R plus P del V0R. This is how what we get. This is how what we get. And again as before, the delta H terms, delta S and delta V are known. At the PT of equilibrium, pressure and temperature are known. So the right hand term is known. Now you see, if I know the right hand term, then this is a constant. At a particular pressure temperature, this is a constant. Now see, therefore, what will happen in this reaction? So this is a constant for a particular pressure temperature value. Now you can see, this you can find out either activity or mole fraction, whatever it is. Either activity or mole fraction, you can find out if you know the composition of ilmenite and know the composition of magnetite. So what you do is, essentially your activity FO2 will become equal to so your activity activity O2 in the fluid phase would be equal to activity of Fe2O3 in ilmenite whole cube divided by activity of Fe3O4 in magnetite squared into 1 by constant PT. Constant PT, 1 by constant PT. Isn't it? This is what it will become to. This will be here and this will be 1 by the constant PT. So you can find out activity or mole fraction if you know the compositions of the phases magnetite and ilmenite in terms of magnetite ilmenite solid solution and magnetite ulvospinel solid solution. If you know the X values, then you can find out the composition of magnetite ilmenite, can find out the composition of magnetite, and then you have a constant, 1 by constant, because here I wrote constant pressure and temperature. So activity of O2 can be found out. So from this assemblage, we eventually found out pressure, temperature, XH2O and XO2. These are the things that we could find out. So therefore, mineral assemblages are used to find out these metamorphic intensive variables. You can ask me why. I think that we should keep as a content for our next video lecture, and then you will find the relevance why. But what I am trying to tell you, that the mineral compositions that you have in an assemblage can be used to find out pressure and temperature, as I told you before. And in this video lecture I told you fluid components can also be found out by thermodynamic manipulation of the reaction, and these parameters can also be found out. Right? Thank you very much. We will continue in the next lecture.